probably aren't familiar with the term radiography. Radiography. Gamma radiation. Where you can fill holes, cooling holes. Radiography is another form of electromagnetic. So we just got done with infrared thermography. That's the infrared. We looked at visible light, visual. And then when we were doing black light, so we're going to be looking at a very short, very, very small wavelength, very high frequency. What happens is that materials, certain materials, other materials do a good job. And so based on those different rates of absorption and the ability of that energy to penetrate an object, we can look at and look inside of something. And so denser materials tend to absorb it more, thinner materials, or denser materials absorb it more, less dense materials have to pass through. Same material, if it's thicker, it's going to absorb it more. If it's thinner, it's going to allow more. And so that's what results in kind of the different shadings in this image, black and white image. So if we look at the spectrum, this one is, I will say, this one is flipped from some of the other spectrums in the thermography lecture. This was actually flipped, where if we look at the visible spectrum, violet was on the left, red was on the right. This is kind of swapped, where the highest, we're looking at frequency here. The lowest frequency on the left, highest frequency on the right, lowest, shortest wavelength is on the right. So X-ray, gamma ray is going to be on the right. And so the range we're looking at here is a frequency of somewhere between 10 to the 18th to 10 to the 20th cycles per second. One followed by 18 zeros. And so it's quite a bit higher frequency, very, very, very small wavelength. And so it has advantages. It's really good. It can have extremely high resolution to detect small flaws. And not only can it detect small flaws, but it can detect those flaws that are inside of it. They can detect, it can be used to detect variations in composition of material. So different materials. And then back in the day when, some of the older test equipment we had, some of the old eddy current testers we had, there's no way to take a screenshot. You have to basically take a picture of the screen, right? Some of our old borescopes, videoscopes, they didn't have it. Nowadays, like our new ultrasound testers, right, we can take a screenshot of it. But X-ray, or radiography, I should say, not just X-ray, but radiography, when it was film-based, it was one of the few methods that created a permanent record directly from performing the method. You didn't have to take a picture of something, or sketch something. Nowadays, most of this is done digitally. You use a digital radiation detector with a plate that's connected to a computer and it can detect radiation. And so it creates a file, just like we can take screenshots from some of our others. So it's not as important, but especially in the past, having these permanent records. There are, however, some serious disadvantages with radiography. The biggest one is radiation is hazardous. no matter what farm you're working in this case, in this range, it is not something that you want to be contacting in large amounts. And so we have to be careful to protect ourselves and protect others that are working in the area to make sure that we don't cause injury from essentially something that you cannot see, you cannot feel, you cannot hear, you cannot taste, you cannot smell. Our senses don't have a way of detecting this radiation. And so it's very easy, if you're not careful and you're not paying attention, it's very easy to accidentally be exposed or overexposed to this stuff without significant controls, procedures, and processes in place to avoid that from happening. Because of that, it requires significant handling and tracking procedures, especially if you're working with radioisotopes, materials that are radioactive, those kinds of things, and X-ray generating devices. There are whole sets of regulations that surround this that are at the federal level. It's regulated by the Nuclear Regulatory Commission. At the state level, there's nuclear regulatory commissions at the state level. There's also OSHA requirements that go into this, Occupational Safety and Health Administration. And so you have to be in compliance and you have to show that you're in compliance with those. So not only do you have to have the equipment, you have to have an entire program in your organization being able to demonstrate that you're using this stuff safely and you're tracking it. In fact, I've looked at wanting to bring this into Western. And first off, just to get a basic X-ray equipment, we're talking about $250,000 for a small part X-ray. The other part of it is because we're fortunate, if I want to bring it in, Western already has an entire department dedicated to radiation safety because it's used in our laboratories and that kind of thing. That division is staffed by 3 people. If that didn't exist and I wanted to bring this equipment onto campus, we would probably have to hire 1 or 2 people just to manage the regulations surrounding bringing this equipment in. So you can see where this is, unless you're using this a lot, or unless you're getting a very big return on investment, being able to make money by performing this stuff, it's not an easy NDT method to deal with. The last part, it's not suited for assemblies that are made from similar materials. So if you have 2 pieces of metal that are similar thickness, similar type, say steel side by side, you're not going to be able to see a big difference between them. You'll be able to see a difference between a crack and a non-cracked area. But it's hard to distinguish things that are similar, that block radiation in a similar manner. So, general principles. The energy of the radiation affects its penetrating power. So there are different types of radiation. There's different energy levels. And so higher energy radiation can penetrate thicker and more dense materials. And so there's kind of a couple ways. So certain materials or certain X-ray generating devices are going to put out higher energy than others. You may have to use them in shorter periods of time, shorter bursts on smaller or thinner components. Or you can get higher energy X-ray devices, higher energy isotopes that can be used for larger devices. And then the nice part with X-rays is, with either one, X-ray or that, is you can vary the time. And so time plays a role. So here you've got a picture of a part. I believe it is an accumulator. I'm not 100% sure, but it looks a lot like an hydraulic accumulator, where you can see the end caps there. There's a piston in the middle, and then you can see the one side is your air chamber, the other side is your fluid chamber. But if you turn your energy up at a higher energy state, you can see and image the caps more without disassembling the object. At a lower energy state, you can do a better job of seeing the body of the accumulator as well as the piston that's left. And so by varying that, you can make that change, or you can see those. radiography, we've got two main radiation sources. So the first are these radioisotopes I've been talking about. And these are the materials that emit electromagnetic waves or waves, excuse me, in the gamma range. The most common one we'll see in aviation and in industry tends to be iridium-192. And so different materials can have different combinations of protons. So the number of protons in a material sets what kind of material it is. But then you can have different numbers of neutrons that are in that material. And that's what sets the different kind of, so iridium-192 has a certain number of neutrons. Iridium-191 has one less neutron, right? So that they're different weights of materials. And so commonly we use iridium-192, which is, it's unstable enough that it gives off gamma radiation, but it's stable enough that the half-life isn't so short that we can't use it. X-ray are things that are man-made. They're generated at the time of use. A lot of you have probably heard the term X-ray tube, which is a form of vacuum tube that generates X-rays, and we'll look at what those look like. But here I'm going to give you a quick refresher course on what I'm going to have this video give you a quick refresher course on what radiation is. Okay. So some of the radioisotopes you'll hear about, I'm sure everyone's heard of, like carbon dating and that kind of thing. Actually, carbon-14 is out there, has an extremely long half-life, so it doesn't. That means it's not going to be useful for our purposes. We want something that has a long enough half-life, or sorry, a short enough half-life that it's giving off a sizable amount of gamma radiation so that we can use it to image something. But at the same time, we don't want something that has such a short half-life, gives off so much radiation so quickly that we can't store it, right? So that the isotope they were talking about, radioisotope she was talking about in the video, and I can't remember which one she said it was, the half-life of only 6 hours there, and it's effectively, after 6 hours, it's a half, after 12 hours, it's a quarter, after 18 hours, it's an eighth, after 24 hours, it's a 16th. That decays so quickly that if we were trying to use it for imaging purposes, we would have to generate it fairly soon, use it soon after generating it. So most of the isotopes we're going to use that we have for industrial radiation, they're somewhere in between. They have a half-life that's short enough that they're giving off radiation where it's going to be useful, but not so short that they basically use up or give off all their radiation too quickly. And so naturally, carbon-14, the ones we usually use, iridium-192, for instance, is artificially produced. Okay, and normally it doesn't exist in nature, but in a lab they can produce it using a particle accelerator or like a cyclotron in order to add or take away, depending on what you're starting with and what isotope you're trying to get. You can add or take away neutrons from the nucleus of the atom to make it unstable, to turn it into a radioisotope. And as I was talking about in the video, it can be, you can add neutrons, you can make it neutron rich where you have extras, or it can be proton rich where you don't have as many neutrons as it would normally have in a stable state. And so as they lose those, the ones we're going to mainly look at are gamma. The alpha and beta particles that are given off during decay, though they are a form of radiation, they're very weak in terms of penetrating. Alpha particles being the largest, they basically can be stopped by things as thin as like a sheet of paper. Okay, beta particles, a little bit more, but still not going to be able to penetrate things like metal. And so that's where we need that gamma, that high energy gamma radiation to be able to penetrate things like metals, thicker materials, and stuff like that. But at the end of the day, the exposure time and half-life must be monitored closely. So in theory, that carbon-14 at the top could, in theory, be used as a gamma source to perform radiography. The only problem is you would need to have your carbon-14 sample and your film sitting near each other with the part in between for millions of years in order for that to work. Okay, because it doesn't give off enough. So that's where we got to understand. So some idea of what we've got, some of the sources that are out there, some other sources. Thulium 170, 128 days. So you can see that can penetrate 13 and a half inches of steel. Iridium 192 has a 74-day half-life and can penetrate upwards of 75 millimeters, 3 inches of steel. Sorry, 3 inches of steel. The first one was a half-inch steel. And so that's the most common one used. And remember, we're not typically using these on steel. They're often being used on aluminum. These gamma ray can penetrate aluminum more easily than they can steel, or composites typically more easily than steel. And so we can be doing thicker, larger parts than if we were doing something made out of steel. Cesium 137 has a 33-year half-life. Okay, low intense, but it's a lower intensity. Cobalt 60, 5.3 years. You can see that has a much higher penetrating power. And then some others, there's selenium 75, ytterbium 169. So we have to pay attention if we're performing gamma radiography, we have to track these half-lives, because we can use, say we have some of the selenium 175 here, or sorry, the selenium 70. You know, it has a 120-day half-life. So the amount of gamma radiation it's giving off in this example, from the day it's created in a lab, okay, when we're 120 days out, our strength, the amount of gamma radiation it's given off has gone down by half. What that means is if we're trying to get the same image the day that selenium 75 was produced versus, you know, we're trying to use it to perform radiography on a part 120 days later, you're going to have to double your exposure time if that's a 120-day-old source of radiation. Okay? Because you got to get the same amount of radiation passing through a part. So you're going to get twice as, when that's new, you're going to get twice as much radiation passing through the part that's new versus the day that it reaches its half-life. And so you would have to allow it, it would have to have a longer exposure time as you get, as a gamma source ages. Okay, so just because it's reached a half-life, a second half-life, it doesn't mean it can't be used anymore. It's just you have to track how old it is and then adjust your exposure time to make up for the fact that it becomes a weaker and a weaker and a weaker source over time. So with our exposure, and we're going to do that, we have to keep track of how much radiation something's getting. And not only are we keeping track of how much radiation our part's getting, we got to keep track of how much radiation we are getting. So if you're in an area where this is being done commonly, where you're commonly doing radiography, you're going to probably have fixed what are called area monitors. If you have a lab space where this is being used, you would install a monitor that would be in there. And these come in different forms. One is airborne. If things become airborne, it kind of works. It kind of sucks in air, monitors radiation, sends it back out. Other things are interlocks, like any of the X-ray equipment I've looked at, or what happens with these radiographic isotopes, these gamma ray isotopes, is they're kept inside of a container, and then that container, typically lead lined, and then that container is opened when we're doing an exposure, and then it's reclosed. Well, you can set up an interlock where you make sure that nobody can be in the area before that container will physically open. Okay? You can set up an interlock where you have to make sure a door is shut on an exposure cabinet before the X-ray tube will energize. It's kind of like your microwave. Your microwave uses a form of radiation generated by a cyclotron similar to an X-ray generator. Okay? You cannot run your microwave. Most of you hopefully can't run your microwave with the door open. Right? You do the same thing with your X-ray machine or with whatever it is that provides radioisotope exposure. And then the last one there, personnel exit monitors. That is, as people go in and out, those actually scan and they see how radioactive you've become. You're working in a lab where these materials are around you. When you're exposed to radiation, as you leave that area, you're going to be giving off radiation. And so you measure the radiation coming off of individuals going into an area to kind of understand how much exposure they experience. Now that's a secondary process that happens afterwards. If something gets screwed up and you get overexposed, by the time one of those scans you, you've already been overexposed. Now you got to deal with the consequences of that. Hopefully it's fairly minor. It might be simply an increased risk of cancer. It may be radiation poisoning, depending on how strong of an exposure you receive. There's also things like portable instruments. There was when we were getting started, we were talking about watching Chernobyl. Everyone saw them walk around with the Geiger counter, the little clicky. It's like a box, there's a little indicator on it that makes the clicking noise. Kind of sounds like dolphin echolocation thing, right? Those are Geiger counters. Those are portable radiation monitors, okay, or survey meters. And all of this is measuring what's called a REM. And the REM is a measure of dosage of radiation. And that can be, you can be exposed to a small amount of radiation for a long period of time. Okay? You can be exposed to a large dose in a short period of time and have equal REM exposure, right? Just like with our image, we got to take into account how strong is the radiation, how long are we doing that exposure. For personal protection, we got to know how strong is the radiation you're being exposed to, how long are you being exposed. And there are one-time limits, there's daily limits, there's lifetime limits. And again, that goes back to if people are working with this stuff regularly, you have to track that as a company or as an organization. And even as an individual, you're going to want to know that. How much radiation have I been exposed to over my career? And that kind of thing. HalfLife is talked about in the video. I've alluded to it. So the radiation, we're looking at radiation is all about statistics. It's will a wave, will a particle of radioactivity contact a cell in my body or contact an atom in a part during a given period of time. And so the likelihood of that goes down by 50% for each half-life. And so as it goes down by half-lives, that's the length of time it takes to get a given amount of radiation will be cut in half every time a half-life passes. Now it's constantly reducing. It's going to be reduced by half after one half-life. So you can't just say, well, from day one to what was the one earlier, day 120, the radiation stays the same, right? It's not at day 120, it instantly gets cut in half. No, it's dropping to day 120, it's at half. It continues today to drop where at day 240, now it's down to a quarter. But it's not like it hits day 120 and it's, okay, now I'm at half. And then day 240, now I drop to a quarter. It's a logarithmic scale of reduction between them. And so that has to be taken into account both for your safety and health, to judge exposure, as well as when you're figuring out the exposure. So we'll leave off there. We'll start looking at actual delivery systems next time, as well as the direct processes.